Thank you very much, Darin, and thank you very much to all the organizers for inviting me to speak at this event. So obviously we all miss Cirm and its beautiful surroundings, but well, we'll do it by virtually. So what I'm going to talk about is joint work with Alexandre Giroir, Mikhail Karpukhin, and Michael Levitin. So let me, just 1 second. So what I'm going to talk about is the relation between the Dirichlet-to-Neumann operator and the associated Spectral eigenvalue problem with the boundary Laplacian. So let me describe the setting. So let omega be a bounded Euclidean domain or a compact Riemannian manifold with boundary. So the dimension of omega is equal to d. And we will assume throughout that the boundary is regular, so at least Lipschitz. And we consider the following Spectral eigenvalue problem. So I'm not sure if it has been already introduced at the school, but just in case. So we're looking for harmonic functions inside omega that satisfy the boundary condition that the normal derivative is proportional to the function itself on the boundary with the coefficient sigma, which is the spectral parameter. So the eigenvalue is in the boundary condition here. And it is known that the Spectral spectrum is discrete, so you have eigenvalues that form a sequence 1 to infinity, and the boundary traces of eigenfunctions, which we'll denote by small un, form an orthogonal basis of the outer space of the boundary. So I just want to make sure that you hear me because I don't see any of you. So do you hear me well?
Yeah, we can hear you. The sound is not really very good, but we can hear you. It's clear.
Let me try. Is it any better this way?
I mean, probably. Yeah, try. Go ahead. I'll tell you.
Okay, so so please interrupt and ask questions because, as I said, so I need to know I'm not taking to the empty space. Okay, so the Dirichlet-to-Neumann map is the operator that has the spectrum that we have seen before. So it's the operator associated to the Spectral spectrum, and it can be defined as follows. So it's an operator that takes a function on the boundary, it takes the harmonic extension of this function, and take the normal derivative of this harmonic extension. So it maps the function to the derivative, to the normal derivative of the harmonic extension. And this operator appears in various applications. So probably the most well-known ones are the electrical impedance tomography and geophysical imaging. So in particular, the celebrated Calderon problem was motivated exactly by these applications. It also appears in problems related to fluid dynamics, such as the sloshing problem, which I'm going to mention briefly today. And there are some other applications to other fields, in particular to differential geometry via the free boundary minimal surfaces, and even to computer science via geometry processing. So the Dirichlet-to-Neumann map will be one of the main objects of our talk today. And let me start with what is known about the Dirichlet-to-Neumann map when we have a smooth Riemannian manifold with boundary. So in this case, so if omega is a smooth compact Riemannian manifold with boundary, then the Dirichlet-to-Neumann map is a self-adjoint elliptic pseudo-differential operator of order 1. And it has the same principal symbol as the square root of the positive boundary Laplacian. So, in particular, using the theory of pseudo-differential operators, one can prove the following sharp Weyl's law for the stack of eigenvalues. So we define what is called the counting function. It's just a number of eigenvalues less than sigma. And you have an asymptotics, and this asymptotics is sharp, so that means that in general, you cannot improve this big O of sigma to the d minus 2 term. So in particular, it's saturated for a ball. And you can rewrite this asymptotics also equivalently as an asymptotics for eigenvalues. So sigma k, they grow as is indicated here with the error term being big O of 1. So these are the results that you obtain from the standard pseudo-differential. Now, we have already said that in the smooth case, there is a very natural link between the Dirichlet-to-Neumann map and the boundary Laplacian. So let's denote the boundary Laplacian. So it's the operator delta m, which has the spectrum, which I will denote by lambda. So lambda 1 will be the 0 eigenvalue, and then we have a sequence of eigenvalues going to infinity. And if we compare the Weyl laws for the Dirichlet-to-Neumann map and the boundary Laplacian, we obtain the following result, that for any smooth compact Riemannian manifold with boundary, the difference between the stack of eigenvalues and the square roots of the corresponding Laplace eigenvalues is bounded by some constant, where the constant depends on the geometry of one. And this is just a sequence of the consequence of this big O of 1 error term that you've seen on the previous slide. So in 2 dimensions, you can actually do much better. And you have the following theorem, which we obtained with Alexander Rohr, Leonid Paranovsky, and David Sher 7 years ago. And it says that for any smooth surface with m boundary components of length L1 and Lm, the difference between the stack of eigenvalues and the eigenvalue, corresponding eigenvalue of the boundary Laplacian, which in this case is just a Laplacian on the disjoint union of circles of the lengths given by L1 and Lm, because these are our boundary components, decays super exponentially as k goes to infinity. And this result is an extension of an earlier result. It was proved by Rosenblum and then rediscovered by Gilman and Melrose for simply connected planar domains. So in other words, in 2D, the difference between the Steklov eigenvalues and the square roots of the Laplace eigenvalues becomes almost indistinguishable as k goes to infinity. So this leads to a natural question. So is it actually at all possible that the Dirichlet-to-Neumann operator equals the square root of the boundary Laplacian? Well, yes, this is possible. This is exactly what you get on a disk. Just by inspection, you see that the spectrum of the disk of radius 1 is just the set of natural numbers with multiplicity 2 with the 0 added in the beginning. And the corresponding eigenfunctions are given by r to the k sine and cosine of k phi in polar coordinates. And naturally, you see that the Dirichlet-to-Neumann map coincides with the square root of the Laplacian on the circle, because sine k phi and cosine k phi are precisely the eigenfunctions of the Laplacian on the circle, and the eigenvalues are given by k squared. So our first result shows that actually this coincidence is really exceptional. And so if omega is a smooth bounded Euclidean domain of dimension greater or equal than v, then one can show that you have this equality only if the dimension is equal to 2 and omega is a disk. And moreover, if the dimension is greater or equal than 3 and the boundary is connected and the Dirichlet-to-Neumann map commutes with the boundary Laplacian, so we require a much less restrictive condition, just that the two operators commute, then it follows that omega is a ball. And the first part of the result in dimension 2 is actually a consequence of is a parametric inequality for the first Stiklov eigenvalue, so it's kind of easy. And the second part is more technically involved and requires some combination of pseudo-differential calculus and some results from differential geometry. So the conclusion is that while the operators are indeed in the smooth case, in particular in dimension 2, they are very close, still they are different, so they cannot really get too close. So what are the questions that we're going to investigate in this talk? So the first question is the following. So we know that the boundary Laplacian and the Dirichlet-to-Neumann map are connected. However, pseudo-differential techniques usually are not very convenient when you would like to express something in geometric terms. So we would like to have a better geometric control of this difference. And another question that we're going to ask is whether these results can be extended to the non-smooth setting. So all previous results were proved under the assumption that the boundary is smooth, and that's exactly the setting in which pseudo-differential calculus works best. Can you do something similar in the non-smooth setting? So are there any questions so far? Do you hear me well?
There are no questions on the chat.
Okay, good. Because I don't see the chat, I see on the list. So it turns out that the problem about the relation between the Dirichlet-to-Neumann map and the boundary Laplacian has been studied more than 60 years ago by Lars Hormander. So he wrote a paper that you can see on the screen, which has actually an interesting history. So this paper was originally written in the 1950s and has been never published. So it existed only as a manuscript that, as I heard from my PhD advisor, Yekar Kanai, who knew Hormander, so this report, this paper was written as a report for some grant, which Hormander actually never was planning to publish. And I knew this paper for quite a while because I had a copy, but I never really bothered to look into this in detail. And then quite recently, the questions about the relation between the Dirichlet-to-Neumann map and the boundary Laplacian has become quite fashionable. So they've been studied in several recent papers that I'm going to discuss in detail later. And I have occasionally found that there is now a volume that is called Hormander's Unpublished Manuscripts. And I found this paper in this volume, and I started reading it again. And together with our collaborators, we realized that actually this paper contains a lot of ideas, somewhat surprisingly, that have been rediscovered in the papers that appeared recently that I have been referring to. So in a way, this paper was ahead of its time, but so let me discuss some of the ideas that appears in it that are quite interesting from the modern perspective. So the key result that is of interest to us in this paper is the so-called Hormander's identity that can be formulated in the following way. So I'm going to state all the results in the Euclidean setting, just to keep things simple. But in fact, in Hormander's paper, it was stated for manifolds, and you can do everything for manifolds. So let omega be a bounded Euclidean domain with a C11 boundary. So this condition turns out to be essential both for the methods and actually even for some results. I will get to that a little bit later. So let U be a function in the Sobolev space H1 of M, and big F be a Lipschitz vector field in omega such that its restriction to the boundary equals the unit outward normal. Then you have the following identity, which relates the difference between the L2 scalar products of the Dirichlet-to-Neumann map applied to U, applied to itself, minus the gradient of the function U, the boundary gradient. So gradient M means the gradient along the boundary. And this can be expressed in terms of this funny integral, which involves the function big U. So big U is the harmonic extension of the small function U. And df is the Jacobian matrix of the vector field. So a priori, this formula doesn't seem to be very appealing, but there is something quite useful about it, namely that what you have here on the right, so let me next slide. So the integrand on the right is a quadratic form in the gradient of U with bounded coefficients, and the coefficients are bounded because we have chosen F to be Lipschitz. And that yields the following corollary, that for some C, some constant C, that depends only on the vector field and nothing else, we have the following bound. And now you can recognize, sort of on the left, you can recognize the quadratic forms that are associated with the Dirichlet-to-Neumann map and the boundary Laplacian. And here you have the quantity that is in the numerator of the Rayleigh quotient for the Dirichlet-to-Neumann map times a constant that is universal. It depends only on the vector field that we have chosen once and for all. And using the variation principle, one can deduce the following estimate. And this is the theorem that has appeared under various assumptions. So first, it appeared in a very nice paper by Rencontres and Stube, which was published in 2018. Then there was another paper by Xung, which yielded the same bound under certain assumptions. And then there was a paper which proved this inequality in a very general Riemannian setting by Bruno Colbois, Alex Gerard, and Asma Hassaneja. So I'm going to describe what they have proved in more detail a little bit further. But these results, they follow from this scheme of Hormander. So let me note that Hormander was not interested in eigenvalue estimates, so he did not prove this result. So he proved this formula and then he moved on to something else. But in reality, So this is the key to the proof of this inequality. So let me make some remarks. First of all, this Hormander's identity is, can be viewed as a form of a sort of generalized Pakhajaev identity, which in turn is also a form of what is sometimes referred to as a Rolich identity or a Rolich-Moravec identity. So there's a whole zoo of identities which are all obtained using some, so there are two ingredients. So you introduce a vector field or something, and then you use some clever integration by parts. So essentially, this identity is a sort of a clever integration by parts. And so Hormander's identity is just a special case of this class of identities, which is particularly useful for this problem. And the identity of this type is also used, so in those papers it is referred as Pakhajaev identity by Provençano, Stubik, Song, and Colbois, Girard, and Hassanich. Now, as already mentioned, Hormander's approach works for Lipschitz domains on Riemannian manifolds. Everything can be extended to that case. And now, of course, everything, what I said, hinges upon the construction of this vector field F. And there is a sort of a canonical way to construct this vector field. So one can take the gradient of the boundary distance function multiplied by some smooth cutoff function in the interior. So note that in the construction, the only thing we care about is that the vector field is normal on the boundary in the C11. So as long as the boundary is itself C11, then you can achieve this by taking the boundary distance function. And in the interior, you can just cut it off and make it 0 because the interior doesn't show up in any way in our approach. And in particular, as a consequence of that, we see that this constant is actually depends not only on the geometry of the manifold, but in fact, it can be estimated in terms of geometric quantities in a small neighborhood of the boundary. And in the paper by Bruna, Alex, and Asma, this approach has been developed, and it has been shown that, in particular, this constant can be shown to depend on the rolling radius of the domain, the bound on the sectional curvatures in some tubular neighborhood of the boundary, and the principal curvatures of F. So we have a very nice geometric control of the difference between the Dirichlet-to-Neumann eigenvalues and eigenvalues of the boundary Laplacian. Now, from these results, we have some application of spectral asymptotics due to the fact that we know much more has been known about the boundary Laplacian than the Dirichlet-to-Neumann map. And in particular, from the results on spectral asymptotics of the Laplacian on non-smooth manifolds, we can show that for a bounded domain with a C2 alpha boundary, where alpha is some positive number, you have the sharp Weyl law for the eigenvalue counting function. And this essentially is an easy consequence of the previous result combined with the results of Zelinsky and Ibri for the Laplacian on non-smooth metrics. And this is an improvement upon a basic small o of c to the power d minus 1 bound that has been previously known due to the results of Agranovich. So the basic bound is known under higher generality, so you just need piecewise C1. So here we need C2 alpha. but here we get a much more precise estimate in the Weyl. Now, for planar domains, and more generally in dimension 2, we can actually prove a stronger result. So we can take C11 planar domains, and in this case, we get the same statement. So the reason is that for planar domains, the boundary Laplacian is once again just the Laplacian on the circle, so we don't care about the regularity for that result. The only thing that we do care is the validity of the Hormander's identity, for which we do need C11, as you remember. And that in particular allows us to extend the known results to the C11 planar domains. And a typical example of a C11 domain is a stadium. So if you take a stadium domain, which has flat parts of the boundary, and then you have circular parts attached to it, so at the junction between the circular part and the flat part, the boundary is C11. And so these domains are now covered by this theorem. Okay, so now let me lower the regularity even further, and let us discuss what happens in case we have corners. So the previous results, unfortunately, do not work for domains with corners. So, and for now, it is not entirely clear whether it's the method that doesn't work for corners or the results themselves don't work for corners. I'm going to comment on that a little bit later. But now let me present some other results, some other approach that covers the case of planar domains with corners. So we consider a curvilinear polygon with angles alpha j, which will be all supposed to be between 0 and pi. And Lg will be the lengths of the corresponding sides, and we could assume that the sides are smooth. So this assumption on the angles is necessary for the methods to work, but we strongly suspect that all the results that I'm going to present on the next slide follow for arbitrary alpha j's. So to a polygon, you can associate a quantum graph, which is built on the boundary of this polygon. So the vertex of the polygon corresponds to the vertices of the graph, and the lengths of the sides corresponds to the lengths of the polygons. And one can consider, so we have the cyclic graph, and one can consider the spectral problem for the quantum graph Laplacian on this graph, the standard one. And what will be not standard will be the following matching conditions at the vertex. So as you see, these are conditions that involve in some form the angles at the junctions. One can check that these conditions are self-adjoint, so you get a nice graph Laplacian on our cyclic graph. And it turns out that this graph Laplacian is actually a good definition of a boundary Laplacian on a polygon. Because from the very beginning, if we would like to extend the results that we've been discussing so far to the case when you have corners, one needs to define a boundary Laplacian. And that becomes a bit tricky because it's not so clear what should happen at the corners. And there are different ways of dealing with it. So a theorem that we've recently proved with Michael Levitsyn, Leonid Parnovsky, and David Scher says that, in fact, the Spectral eigenvalues of a curvilinear polygon, they are small of 1 away from the square roots of the eigenvalues of the associated quantum graph Laplacian that I have just shown to you. So, in particular, it is natural to choose this particular quantum graph Laplacian as the boundary Laplacian for the polygon in dimension 2. The proof of this result is very involved. I'm not going to talk about it. I just mentioned that it is related to the sloshing problem, so the problem of the oscillation of fluid. I don't know if you see me sloshing the water in my glass, but that's exactly what the sloshing problem is describing. So, so the techniques used for the proof of this theorem are very different from what I have presented so far. But my point is that there is a way to define nicely a boundary Laplacian for planar domain with corners, and this Laplacian is this quantum graph Laplacian that you can see. Now, the last topic that I'm going to cover in my talk is the Dirichlet-to-Neumann map for the Helmholtz equation. So, suppose that mu is not a Dirichlet eigenvalue of omega. Then we consider the following boundary value problem. So we consider the Helmholtz equation with the parameter mu in omega. And then we do the following. So, so we know that for every u in the solid space h1/2, there is a unique solution of this problem, which I will call u mu. And precisely for the reason to have this unique solution, we made the assumption that mu is not Dirichlet eigenvalue. And we will call this u mu the mu Helmholtz extension. In particular, if mu is equal to 0, then we just get the usual harmonic extension. And we can define the Dirichlet-to-Neumann map for the Helmholtz equation, which maps the function u to the normal derivative of its Helmholtz extension. Here is an example. So what is plotted here are the eigenvalues sigma mu k of the Dirichlet-to-Neumann map d mu for the unit digit. So now we have two parameters. So we have a parameter mu that is the Helmholtz parameter, and we also have the parameter k that is the index of the eigenvalue. And you get a very nice picture that, so I will comment a little bit what is drawn here. So as you can see, so you have branches of eigenvalues. So different branches are colored with different colors. And all these branches come from minus infinity. So when mu is negative, then things are very nice. And so these branches go like that. And then what happens when you hit a Dirichlet eigenvalue for the first time? So the Dirichlet eigenvalues correspond to the asymptotics here. Yeah, so the dotted vertical lines, the asymptotics correspond to Dirichlet eigenvalues. And there you get a discontinuity. So you have a branch that goes to minus infinity, and then it reappears at plus infinity. And the zeros that you see on the mu axis, so that is the axis sigma equals 0, these are the Neumann eigenvalues. So the Neumann eigenvalues correspond to zeros on this axis. The Dirichlet eigenvalues correspond to the asymptotes. And the Steklov eigenvalues, well, they naturally correspond to the case mu equals 0. So the Steklov eigenvalues are here. Okay, so all these intersections give you the Steklov eigenvalues. So somehow this picture, well, it's not very simple, but the advantage is that it captures all spectra, so Dirichlet-Neumann and Steklov simultaneously. And you can ask the same question. So what is the connection between the Helmholtz Dirichlet-to-Neumann map and the boundary Laplacian? And we have the following theorem that is proved in a similar way as the result that I presented before. So if you have a bounded domain with a C11 boundary, and you assume that the parameter mu is negative, so this is essential, as you have seen, for negative mu's, things are going much better than for positive. Then there is a constant that bounds the difference between sigma mu k and the square root of lambda k minus mu. So once again, sigma is the eigenvalue of the Dirichlet-to-Neumann map. Lambda k is the corresponding eigenvalue of the boundary Laplacian, and mu is the Helmholtz parameter. And what is interesting about this bound is that it holds uniformly over all mu's that are negative, 0, and all k's. Because this C actually depends only on the vector field that we have. And here's another example, and here's an illustration of this observation. So if we look at these quantities for the unit disk, and here there are two regimes that you can see. So here sigmas are small and mu's are small, and here sigmas are large and mu's are large. And as you see, in both regimes, the dashed lines and that correspond to square root of lambda k minus mu, and the solid curves that correspond to the eigenvalue sigma mu k, they lie at a fairly controlled distance from each other. So clearly they're away by a constant. Now, let us recall that the Dirichlet-to-Neumann map for the Helmholtz equation is closely related to the Robin boundary value problem. So there is a so-called Dirichlet-to-Neumann duality, which I'm going to state in the following form. So let's consider the following problem, which, depending on your how you would like to view it, it could be viewed as a Helmholtz Dirichlet-to-Neumann problem or as a Robin problem, and that's precisely what we're going to say next. So here sigma can be viewed as a spectral parameter, and mu is a given parameter, and in this case, this is the Steklov problem for the Helmholtz equation. Or it could be viewed as conversely. So now mu can be viewed as a spectral parameter, and sigma can be viewed as a given parameter. And then you think of mu sigma k as the eigenvalues, and then there are the eigenvalues of the Robin Laplacian with the boundary condition given here. So basically, one is sort of an inverse function of the other, if you wish. And that is quite useful in various circumstances, and it has been applied by many people. And in particular, it turns out to be useful for us because there are various results about the Robin eigenvalues as that we can make use of in our study of the Helmholtz Dirichlet-to-Neumann map. And in particular, what we observe, and that was sort of a surprise for us, that in this problem, there is certainly something that fails when you give up the C11 assumption. With the Steklov problem, once again, we need the C11 assumption because of the method, but it's not so clear whether we need it indeed for the validity of the results. So here there is a result, namely the uniformity of the bound that we have mentioned before, that fails. And the reason why it fails is the following. So there is a very nice result due to Magda Khalil that states that if omega is a curvilinear polygon with at least one angle less than pi, then you have the following statement. Well, I'm presenting a simplified version of this result. But basically, it says that when you take the asymptotics of the Rabin eigenvalues as sigma goes to infinity, then there is a certain finite number of eigenvalues that have a different asymptotics. There is a different coefficient in front of the main term of the asymptotics than all the other eigenvalues. And that's caused by the presence of angles less than pi. And if you reverse this result, then you see that this bound cannot hold uniformly. And it doesn't matter which choice of a boundary Laplacian you choose, because you choose it once and for all eigenvalues. So this doesn't work. It doesn't work because it cannot work for small and large views at the same time. And therefore, there is a limitation to this uniformity, so that you do need the lack of corners, in particular, the C11 assumption. So let me conclude with some further results and open questions. So, in fact, you can play this Hormander-Pakhajaev identities in other settings, in particular, what we have done with the collaborators. We considered the Dirichlet-to-Neumann operator on forms, and there is a relation between the eigenvalues of the Dirichlet-to-Neumann operator on forms as defined in earlier. There are several definitions. In fact, so the one that we've been using is due to Misha Karpukhin. So there is a relation between the eigenvalues of this operator and the Hodge Laplacian on the boundary. And in particular, this allows us, again, using the results for the Hodge Laplacian, to prove Weyl's law for this Dirichlet-to-Neumann operator forms. So let me note that this particular operator that we've been using, the a priori, it's not even known that it's a pseudo-differential operator, and therefore there was no Weyl law known for it previously. So for planar domains, going back to the very first beginning, the very first result that I've mentioned, I remind you that we've proved that if the Dirichlet-to-Neumann map coincides with the boundary Laplacian, then it has to be a disk. However, for the result that dealt with the commutation condition, we needed dimension greater or equal than 3. And the reason we needed the dimension greater or equal than 3 is that we've used certain properties of the certain geometric properties of the domains, in particular the and also we've used the fact that the subprincipal symbol of the Dirichlet-to-Neumann map in dimensions d greater or equal than 3 is non-zero. So in 2 dimensions, it's always 0, and our method fails. However, it is still quite likely that the commutation of the Dirichlet-to-Neumann map and the boundary Laplacian is quite restrictive in dimension 2 as well. And the natural conjecture is whether it holds only for a disk or for a rotational symmetric anodes. So we know that in this case, it's just by calculating the eigenfunctions, the separators commute. Is this all, or there could be something else? A question that is motivated by the discussion of the quantum graph as a boundary Laplacian for the polygon, and I think this is a very important question. What is a good definition of the boundary Laplacian for domains with edges and high dimensions? And finally, let me mention a very old question, not very old, but at least a year-old question that I learned from Polterovich at the time. So the question is to prove Weyl's law with any remainder on Lipschitz domains. So if you remember, I've mentioned the result by Polterovich himself, who proved a rough Weyl law for domains which were piecewise C1. So that's the best we know. So for Lipschitz domains, somewhat surprisingly, we don't have even a rough Weyl law for Stiklov eigenvectors. And proving it would be certainly very interesting. So this question of Polterovich is open even in 2 dimensions. But even in 2 dimensions, we don't know the validity of Weyl law in the Lipschitz set. Thank you very much for your attention.
Well, thank you very much, Iosif. It was a very nice talk. And now it's time for questions. There are people already they registered on the chat. So Jean, would you like to ask your question?
Yeah, so on the slide earlier, you said that Hormander's result extends to Lipschitz domain in Riemannian manifolds, and then explain how to get a C11 normal vector field for domains with C11 boundary. So how do we expand Hormander's result to Lipschitz domain specifically? How do we get the?
No, maybe it was you need C11. So you do need C11 boundary. What I probably mentioned is that the metric is Lipschitz.
Yeah, okay.
Yeah.
And okay. I had a second question, if I may.
Mm-hmm.
So this this commutation result, does it have some sort of rigidity property if you don't assume that they commute, but that the commutator would be very small in some sense? For example, if the commutator between the Laplacian and the Dirichlet-to-Neumann map is some pseudo-differential operator of order -s, can you say that you are close to being a ball in some sense?
So we've thought about it. That's a very good question. Yeah, so it's well, I don't know the answer, but it's certainly it's kind of a stability question. Which is,
yeah.
Yeah.
Okay.
Are there any other questions or comments?
Yes, about the condition that the boundary Laplacian and the Steklov operator are the same. So for planar domain, you said that it was only on the disk, but what happens if you are on a general surface? For example, with annulus, is it a catenoid or is it?
You mean the equality or?
The equality.
Well, the problem is that if you have several boundary components, then your Laplace spectrum will have several zeros, right? So it immediately rules out the equality with the Steklov.
Okay.
So if you take the ball with 3 dimensions, you will not have equality between spectra.
No.
And then you have in 3 dimensions, it's natural then to ask what would be the shape, the geometry, which give you the lower constant C there, no?
True, yeah.